Hey kids, we're going to talk about linear regression, part two. So hopefully you watched already part one or you're part of the part one lesson, but this is for the day after the first day of linear regression. Here we have data from 27 students' test scores on two different exams. So here's unit one, which is designing studies, and here's unit five, which is probability, which is coming up next. This is the line y equals x. And you can see that the majority of our data is to the right of the line y equals x. So take a second, pause the video, consider the statements, and decide which of the statements are true. And hopefully you've had a chance to talk about those, and then we'll go through them. So every student performed better on test one than test, well, there's a few that did not. Anybody that did better on test one than test five would have a higher x value than a y value, right? So they'd be right of this line. But here this student got approximately like an 85 maybe on the first test, but almost 100 on the fifth test. Every student performed better on test five than test one. All of these are counterexamples of that. Most students, but not all, performed better on test one. That's true. Most students did do better on test one. Most students, but not all, that's the opposite. Association between the scores on the two exams is negative. Well, this looks like a positive association. As we go to the right, we're going up. There's more variability in the distribution of scores for test one than test five. Well, let's look at that. Variability. The scores for test one range from 60 to 100, right? Maybe the 102s that you could get if you got all the points. 60 to 100 is about 40 points. The variability on test five goes from about 40 to 102. So we got 60 points. So there's more variability on test five than test one, which may mean that probability is a difficult unit, but that is really going to be up to you. Okay, so we're going to take a second. This is on our formula chart. And if you don't have a formula chart, they're in Schoology, linked in the handouts. We don't use them all that often, but they do come into play here. So if you open up the handouts in Schoology, you're going to see this. And this document has lots and lots and lots and lots of things. And it's 2 pages, so you can see. But we're really looking at, it's right at the beginning on the first page, and we can see a few things. First of all, R, the correlation coefficient, and here's a terrible equation that we'll never use. We also have y hat equals a plus bx. This is the one that I told you, choice 8 in the calculator, right? Y hat equals a plus bx. B is the sample slope. Y bar is equal to a plus b times x bar. And you might notice that our slope, b here, is equal to r times the standard deviation of y divided by the standard deviation of x. Now, these are very specific pieces of information that they're giving us. And really what we're looking for are places where we have enough information. If we get stuck in a problem, at the very least, we're hoping that we have enough information to use these formulas if we can't do anything else. You'll also notice, right, we have the slope, b is equal to this, and then a is the y-intercept. I can solve this for a equals y bar minus b times x bar, right? And y bar and x bar are just the average for the y values and average for the x values, and b is still the slope. So I need to know the b. And then standard deviation of y's and x's, means of y's and x's, and the correlation coefficient r, which we're not going to use this one ever, but they'll give it to us in a computer printout, which is what we're going to learn today. Okay, so back to this. B naught is our y-intercept, b sub 1 is x, and these are kind of old because they don't give them to us like that anymore on the, you saw the formula. So here we go. Is a linear model appropriate? What we want to know is, should I even be using a linear model to model the data that I have? If we go back to our model that we had way back here, does this look linear? I'm not saying that the y equals x line is a good model, but does this look linear? Do we have a line that goes through here? Well, probably. And our y-intercept would be negative by a lot if we try to use a line. But we could probably model this data with a line. But what we want to look at is a line appropriate? So first of all, is the scatter plot fairly linear? That's what I just went back and looked. Is the scatter plot linear? Looked like it. Is there a pattern in the plot of the residuals? Now, what I needed to look at is the residual plot. And we're not going to be responsible for making those, but we are going to be responsible for interpreting those. So when I look at the residual plot, what I'm looking for are really two things. I'm looking at any kind of U-shaped pattern, which in my residual plot, I don't see a U shape. And I'm also possibly looking for fanning, which honestly in this one, there could be potential fanning in this graph, but probably not. So I'll talk about fanning in a second, but really in this, I don't see a U-shaped pattern, either upside down or right side up U, which tells me that it wasn't linear to begin with. Now, we talked about residuals at the end of last lesson, and if you missed it, go back and watch the earlier video. You can fast forward. But we don't want a pattern in the residual plot, and I don't really see one. Fanning happens when we're looking at the plot and it looks like there's not equal variation. We want all our points to be about the same distance away, and it looks like there's more variation here in the upper part of the graph than the lower part. And specifically, fanning would be that they tend to narrow as we go. So it looks like a fan, if you would. This is not a great example of fanning. We just have less values observed as higher protein values. So there's just more data down here. And I don't know if I would consider this to be fanning necessarily, but I'm always suspicious. Ooh, does this start to taper? If it does, we have fanning, which means that our predictions are good at some places and not so good at others. And we want equally valuable predictions, either all consistently good or all consistently terrible, where we know we need to adjust for those predictions a little bit. All right. So the residual plot that does not have a distinct pattern, so it looks like our linear model would be appropriate for this protein versus fat model that we have here, or even for the one that we had before if we looked at the residual plot. Sometimes you might look at this and say, oh yeah, that looks fairly linear. As a matter of fact, our R value would be really, really, really close to 1 here. We put a line on it. Oh, that looks really good. But when we look at the residual plot, you can clearly see a U-shaped pattern. This might have been like really slow exponential growth or power function, something like that. So look at the residual plot. Residual plot will tell us probably more than the actual scatter plot will anyway. Is the scatter plot linear? Great. Still, maybe not trust it. Look at the residual plot if you have it. Residual plot that has no pattern is an indication that the linear model might be appropriate. So here's a random residual plot. That's what I'm looking for. And if I'm going to write about this, I may say, because our residual plot appears random, our linear model is appropriate. Here I have a clear U-shaped pattern to the residuals. And if that happens, then I would think that a linear model may not be appropriate. It's probably something else, power, logarithmic, exponential, something. So note about residual plots. This is really important. Here's our normal scatter plot, calories versus total fat. And here's total fat hat, right? This would be a hat. Total fat hat equals 0.0553 times calories minus 4.8. And then we have an R squared of 0.75. If I wanted to know R, I would take the square root of both sides and notice the slope is positive and make sure that my R value is positive. Anyway, we're looking at this. If I look at the residual plot, we would keep our X variable And then the y variable becomes the residuals, the distance from the line. And you can see that this looks like if I just took the line and tilted it and made it at 0. So these 2 points here are these 2 points here, and the scale gets blown up a little bit because the distance is a lot more measured. We can also look at the residual plot and we can see predicted total fat, and those look exactly the same. So predicted total fat, this is the y hat values, are prediction values, and the graphs look similar. Notice the scale's different, but the graphs look similar. Still no pattern. That would be different than if I looked at the residuals versus y. If I just put the total fat there, that's not a good residual plot. That's not going to tell me anything. I don't want to use that. Least squares regression line. Consider the following 4 points. Here we got 4 points. How do we find the best fit line? Well, we call it the least squares regression line because it's the minimum of the sum of the squared residuals, because some residuals are positive and some residuals are negative. If we just added the residuals themselves, we get 0. But if we square them, we get a positive value for all of them. And the line that goes through these 4 points is the line that would give us the smallest sum of those squares. So facts about the least squares regression line. These are things that you might want to know for multiple choice questions out in your future. For example, the sum of all squared residuals is minimized, which is what I just said. If we didn't square them, the sum of all the residuals is 0, which is also what I said a minute ago. It goes through the point x bar, y bar. So every least squares regression line has a point on it that is the average of the x's, 1, 3, 5, and 7, divide by 4, and the average of the y's. That point is on the line. So if we're going to build the regression equation, we take the average of the x's, we take the average of the y's. We know that this point is pretty much a hinge. Every line would have to pass through it, but we want the line that's going to give us the least sum of the squares, and there it is. The slope is equal to r, our correlation coefficient, times the standard deviation of the y's, divided by the standard deviation of the x's. You will never ever have to do that by raw data alone. We would give you some summary statistics. So all of this we talked about, we're going to actually use the values that are on our formula chart instead. So we don't have b and b naught, but we have a plus bx. B is here. Here's this. Remember, we're going to solve this for a, which you can see back on the PowerPoint. Y bar minus the b sub 1 is the slope. Slope times x bar. It's exactly what we talked about. So in this case, here's our a, and here's our slope, which is b. And this is a plus bx on the new formula chart. Okay. So if you get a summary of values, such as this summary of values, and we have x bar and we have y bar and we have standard deviation of x, and we have standard deviation of y, and the correlation coefficient, you may be asked to use the formula to come up with the equation. So we're putting that in. I think there's a question in the homework for that. It wouldn't be a bad idea to take a minute, pause the video, and practice those now to see if you can use the formulas that were in the formula chart and come up with these. So hopefully you did that. I'm going to scoot this on up here and do the first one just to make sure that you got it right. So our slope here, b, is equal to r for the first one, which is 0.5, times the standard deviation of y, which is 3, and the standard deviation of x, which is 2, and 0.5 times 1.5 gives us a slope of 0.75. Half of 1.5. I didn't even need a calculator for that, really. And then on this one, remember that a is equal to b, which we just found, times x bar minus y bar. So my A value is equal to 0.75 times x bar, which is 10, so 7.5, minus y bar, which is 20, and 7.5 minus 20 is negative 12.5. So I have y hat equals negative 12.5 plus 0.75x. Okay, we're going to talk about computer printouts. And there's a worksheet that you can go through with this here. So we're not saving the rest, but I'm going to pull the worksheet up. And what I want you to see is, let me get this worksheet here. Oh, okay. So we're going to look at the computer printouts here, and we're going to do the same thing that we were doing before. And you have your notes from last time. Hopefully, you guys went and took really good notes. And remember that on the back of this note sheet, there's a cheat sheet of all the sentences that we're going to use. So if you need that cheat sheet to write your sentences, use it. I strongly suggest that you know what your sentences are going to be without the cheat sheet soon enough. But here's a computer printout. This is what these are going to look like for us in general. So I have X and Y defined already for us, which is nice. Treadmill time and ski time. And then we're looking at a lot of stuff that the computer just spits out to us. Here I have a scatter plot. Often I'll also have a residual plot. Notice that I see a linear pattern in the scatter plot, so I think a line is appropriate. And we look for the slope. So there's two variables that we have here. One of them says constant. The other one says treadmill, and you can see treadmill goes with the x, and in front of x is our slope, so this is going to be our slope. Also, constant is not changing. That's our y-intercept. So I have that. So the slope, what is the slope of the equation? The slope is negative 2.3355. You can also see this has a negative slope generally and a positive y-intercept that would probably be around 88. So if you use your general understanding of algebra, you can kind of figure out which one it's going to be. Also, the y-intercept, 88.796. Write the regression line in context. So we're going to say, okay, well, y is ski time. So I'm going to put ski time here, ski time, hat. Ski time equals negative 2.3355 times treadmill time plus 88.796. Notice that I have my y and my x here, even though we defined them up here. And if we did, we could use y and x again, but it says in context that I did it. Okay, now we're going to scoot down here a little bit and try not to lose any information that we really need. Interpret the slope in context. Now, again, we could be looking back over at our cheat sheet here that we have for last time and trying to find our slope equation and do all of that. You really need to try to wean yourself off of that as soon as possible. But remember that slope is rise over run. And I'm going to think of this as a fraction. And I'm saying, okay, well, if I have rise over run here as change in y over change in x, as my change in y happens is this, my change in x is always going to be 1 if I make this into a fraction. So my sentence looks like that. I'm going to say as x is treadmill, time increases. Oh, wait, first of all, slope equals negative 2.3355. Now they just asked me that above, so I probably wouldn't have to write that again if it's that close, but generally rewrite slope. So I have that. And then as treadmill time increases by 1 minute, ski time decreases. Oh, wait. I'm going to back up here, kids. So we could say on average or something like that, but what we're really saying is the model predicts ski time decreases by 2.3355 minutes. So as x goes up by 1, we're going down by 2.3355 minutes on average. So we're saying the model predicts is telling us, hey, it's not guaranteed. We're just expecting that on average, we're going down by that much every time we go up by a minute. Notice I said decreases here and I didn't put a negative. You don't want to have a double negative. Okay. Number 2, certainly plausible that workers are less likely to quit their jobs when wages are high than when they're low. So let X equal the average hourly wage and Y equal quit rate. So this is happening right now, as a matter of fact. As wages go up and jobs are more plentiful, people are more likely to quit the crappy job they had than look for a better one. So we're looking here again. We have coefficient, we have wage. Wage goes with X. And Y is our quit rate. But we are looking here, and here's my X. So this is going to be my slope. And my coefficient here, this is Y intercept. Wages are, as wages go up, people are less likely to, I think I said that backwards. Right now, wages are high and people are leaving their jobs, but it's because they can go find better wage jobs. But if you're getting paid a lot, you're less likely to quit your job when wages are high than when they're low. For you, that makes more sense. I think I thought of this backwards. All right. Anyway, here we go. Kids, this is only like the 10th time I've ever done this worksheet. What is the slope for the regression equation? All right, so we find the slope, we find the y-intercept, slope goes with wage goes with x. So whatever is the x value here is going to go with our slope, and that's the important thing that we understand. So slope, negative 0.3466. Notice that we didn't get a scatter plot or a residual plot this time, so we're just going to have to go with the data is a linear form for this one. The y-intercept, 4.8615. Write the regression equation in context. Okay, so quit rate hat. Predicted quit rate. I always feel bad when I write these things because Mr. Yoon's handwriting is so much better. Predicted quit rate is equal to negative 0.3466 times our wages plus 4.8615. Interpret the slope in context. Again, when we think of this as a fraction over 1, as x goes up by 1, y goes up by this much, and it's actually going down, right? So as wages increase by 1, what do you think? It's average hourly wage, so dollar per hour. So $1 per hour. Quit rate. Oh, wait. I did it again. The model predicts. Quit rate decreases by 0.3466. What is the correlation coefficient? Correlation coefficient is R. So we look up here, and I don't see R, but I see R squared, and I also see this R squared adjusted. And I'm going to tell you right now, R squared adjusted, it's a trap, kids, it's a trap. Run. Don't use R squared adjusted. It always sounds like the new and improved R, and some people think that must be better, but it's not. So we change R squared to 0.729, and I'm going to take the square root of 0.729, and I get 0.854 when I round. But I got to decide, because I took the square root, is it positive or negative? Well, the R value, the sign on it, is always going to match the sign on our slope. And since our slope is negative, our R value is going to be negative. And so then we got to hit strength, form, and direction, right? Now we're told linear form. We got to think about what 0.85 would tell us. And so R equals negative 0.854. There is a strong negative linear relationship. So it tells me that. Between wage and quit rate. R squared is our coefficient of determination, and we leave that as a percentage. So R squared equals 72.9%. And this is that variation sentence. So go back and you look at your cheat sheet or something, and we're looking for the percent of the variation in Y that can be explained by the linear model, blah, blah, blah. So here it is, 72.9% of the variation in Y. Y is our quit rate. Can be explained by the linear model for wage, and this is like average hourly wage, and quit rate. And the last one is SE. What? SE? Well, remember, S is the standard error of the residuals. Maybe you don't remember that because we haven't talked about it, but this is the standard error of the residuals. So this S is telling us how much our error, our residuals, if you remember back to the notes, error is equal to Y minus Y hat, actual minus predicted. This is the standard error of the error. So when we're talking about that and we're trying to interpret what does that mean, it's the typical difference between the observed and predicted values. How much do we vary from our prediction typically? Okay, so in context, 0.4862 is the typical difference between observed quit rate than predicted. So we think we're going to vary by that much typically between where our points are and where our line is. So we have an idea generally of what's the space look like between the points and the line that go through it. And typically that's varying by 0.4862. All right, kids, there's a whole nother side to this with handspan and average age. And I want you to fill those out and then you can check in class